Hi, my name is Mokhwa in AMS department. My father is in Science department. And today, the topic that I wanted to introduce is the Quasi-Newton method. So the word quasi means that it being partly. So actually, this Quasi-Newton method partly mimics the Newton's method. So let's give the analogy of this graph. So let's assume that you are in the mountain and then you want to find some town and you want to drink the Coke. And actually, the Coke is here. The town too. But actually, if you are here, starting from here, you are good with just drinking water because you're really thirsty. So the first goal, if I'm in the mountain, is to get to go to the town which is nearest to me, which is the local minimizer. And I want to go to a descent direction. That means that I want to go down and down from the mountain. So that's called the gradient descent. That means that I just use the gradient information, the gradient of fxk. But this is really slow because you just want to pick the slope from the mountain, which is pretty not steep that much. So it's less burden, but at the same time, you have to take a lot of time. However, in Newton's method, you want to take a shortcut. That means that in the real minimization problems, you have to compute the Hessian matrix, which is nabla fx, but it is kind of computationally burdensome, and it's really hard to compute within a short period of time. So the Quasi-Newton method wants to combine this gradient descent and the Newton's method just by approximating the Jacobian or Hessian matrix. So this is the simple analogy in two-dimensional problem. So you use the second order Taylor expansion at the point of x. So here x can be x1, which is the previous point, and we want to compute the exact slope at x2. So in Newton's method, we have to exactly compute this f double prime. But what we do in Quasi-Newton's method is to estimate this blue line with the red line by just interpolating with the previous information x1 and f prime x1, and the current teacher x2 and f prime x2. So in this way, we have to solve this kind of system of equation. And in the high dimensional problem, which is called second condition there. So actually, second condition is underdetermined. So that means that we have a bunch of Quasi-Newton's method, not only one. There could be various of Quasi-Newton's method. And so it's blocked, but there are four Quasi-Newton's method, and the BFGS is the most famous algorithms in to solve the minimization problems. And the most important in BFGS method is that the approximation is positive semi-definite. So that means that if you're in the mountain, you want to go down and down. You don't want to go to up to find somewhere the town that has the Coke, So yeah. However, the another Quasi-Newton's method other than BFGS does not necessarily satisfy the positive semi-definite. So actually, we may blow up at some point. That's the kind of disadvantage of using other than BFGS. However, there is another Quasi-Newton's method which is multi-secant. It's actually multi-secant should be there, but I don't know. Yeah. But anyways, yeah, there is multi-secant method. That means that we not only consider just one previous information, but we also at the same time consider different multiple information at the previous times. So in this way, we may consider the momentum as well, because if you're in the mountain, you don't want to take the route which you don't want to go, So yeah, so my goal in my project is to combine the Newton's method, BFGS method, which guarantees the positive semi-definite of the estimation, but at the same time consider the multiple previous secant conditions, so that we have to solve this kind of system of equation. However, the thing is that if B is positive semi-definite, that means that whatever we multiply the matrix in front of this BS should be positive semi-definite. However, it should be symmetric. However, if we multiply S in front of the Y, it does not necessarily to be symmetric. So actually, this problem is infeasible. So in this way, so at this point, we have to solve the relaxation techniques or positive semi-definite programmings to find the feasible set to get the approximation. Yeah. Thank you.
In practice, say thinking about BFGS, you end up needing to combine it with like a line search and step restriction and other things. So how does your approach work in that respect?
So actually, generally we don't need to do the line search because BFGS has the matrix B. So for example, like estimation, which is quasi-standard definite that guarantees the descent direction. So maybe line search can help you to find better direction, but it does not necessarily use. But however, the other methods, like broadens or like multi-sequence or other methods actually does not guarantee the quasi-standard definite. So that's why we wanted to push that Hessian matrix B onto the positive definite reason. So, however, if in that case it's usually infeasible to solve the problem, so that's why we wanted to relax the constraint so that we can find the B, which is positive standard definite, but at the same time satisfy the constraint to guarantee the decent direction. Yeah, you want to drink the water.